Hello, my name is Lindsay Broadway, and this is Physics 2212, Experiment 4, Magnetic Braking with Faraday. So for the introduction, the purpose of the lab is to show how the magnetic force counteracts the force of gravity. The magnetic force is induced since the dipole falls through the tube of aluminum foil. Some models and principles used are the magnetic field of a bar magnet, which is given to us on our formula sheet, the magnetic flux equation, Faraday's law, which is in the upper right-hand corner here, and then Ohm's law, Lenz's law, which talks about the direction of the induced current, and the momentum principle, also Newton's second law. The preview of this experiment is that the magnet took about 1.29 seconds to fall, and the model took about 1.84 seconds to fall. So pretty close, but not exact. The system was the bar magnet, and the surroundings are the roll of aluminum foil on the Earth. The initial conditions are that the bar magnet falls from rest, so initial velocity is 0, and at a height of 0.32 meters. And on the right, you can see my free body diagram where the magnetic force is pointing up from the induced current and the force of gravity is pointing down. So this ends up slowing the magnet down on its fall. So for the experiment, here are the initial measurements of my bar magnet and the aluminum foil. So as I said before, the average time that it took to fall after 5 trials was 1.29 seconds. Some quick checkpoint questions were, what if the aluminum foil tube was replaced with a ferrous tube? And the ferrous tube would actually become magnetic, so the magnet would stick inside of it. And then what happens to the magnet as it falls? It takes much longer because the magnetic force is counteracting the force of gravity. So for the code, the first two pictures at the top are just me setting my initial variables for the length of the tube, width of the tube, mass of the magnet, and mu of the magnetic dipole moment. And then the first function is the magnetic field of the dipole as it falls. And then the second part is finding the change in flux over time. And these are just kind of inputting our variables into the formula and getting an output. And then the last part is that the ring current is the negative of the flux over the radius of the ring, which is Lenz's law and Faraday's law. The next part is the force of gravity being negative mg, and then the second image is just kind of like updating the magnetic field as the magnet falls. And then the last image is updating the net force. So it's the force of gravity and the force of the magnet. And then the last part is using Newton's second law and the momentum principle to update the velocity and the position of the magnet as it falls. So the results of this lab, as I said, the computational time was 1.84 seconds. You can see this down at the bottom. You can see the graph of velocity versus time, and then also on the top, a kind of physical image of what the magnet looked like as it fell. The experimental time was 1.29 seconds after 5 trials. I think that the difference between these two is due to incorrect timing. It was a little bit of a struggle for me to film and drop the magnet and time with just 2 hands, and also air resistance, so there is drag as the magnet falls through the aluminum foil tube. Some of the questions, the first one was about the colors of the computational experiment. So the blue was clockwise and the red was counterclockwise. And how I figured this out was I knew by the right-hand rule that it had to be blue and red, like clockwise and counterclockwise, to slow the fall, because if it were opposite, then the magnetic force would be pushing down with the force of gravity. If you switch the magnet, the blue and red currents would switch and it would still fall slowly because they are induced. So the difference between the real world and the computational result, they were different. To make the computational result better, we could use a smaller delta t, so get more precise increments of time, or use more rings through the tube as the magnet fell. And then the forces are not balanced at the beginning and end of the magnet's fall, which is shown on the velocity versus time plot. But in the middle, they do cancel out, so the velocity is constant, so that would be the terminal velocity. And then finally, the discussion questions. The induced force would completely cancel out with the gravitational force if the resistivity of the conductor were reduced to 0, so the magnet would be stuck in the tube completely. And if there were holes in the tube, the current would be blocked, so the magnet wouldn't feel as much force, so the magnet would fall faster. This is my lab 4. Thank you.